part of a course on subRiemannian geometry. Now I will revise the notion of Hausdorff measure, and then I will prove that if a metric space admits a measure for which each ball of radius r has measure that is comparable with r to the power q, then the space has Hausdorff dimension q. The Hausdorff measure can be defined for any metric space, actually for any subset of a metric space. So let's say we have MD a metric space, and we consider a number, a real non-negative number, and whenever we have a subset of the metric space, we first define the Hausdorff content. So for given positive delta, we define the Hausdorff two-dimensional delta content of S to be the infimum of all possible sums of diameter to the Q. So this is an infinite sum, countable. So where the EIs give a covering of S, and the diameter of the sets are all bounded by delta. Okay, the Q-dimensional measure Hausdorff measure of S is defined as the supremum of delta, strictly positive, of the Hausdorff delta content of S. So this fact is actually, first of all, this supremum is the same of the limit as delta goes to 0 of the delta content. And it's true actually that this Q-dimensional Hausdorff measure is indeed a measure, is a Borel measure. Okay, so now let's see how these measures depends on the parameter Q. So this is important fact that there exists actually a unique exponent Q0 between 0 and plus infinity, such that for all Q less than Q naught, then we have the Hausdorff Q measure of the set S is going to be infinity. Instead, for all Q greater than Q0, then we have the Hausdorff Q measure of S is 0. So in other words, as a function of Q, the Hausdorff measure are always infinity. So this is plus infinity. Then they jump, and then are equal to 0. And there is a unique value Q0. Q0 is not, we don't know if it might be 0, might be plus infinity, or maybe be finite. Okay, so we define. So we call this Q0 the Hausdorff dimension of M. So in particular, right, we are saying that if that HQS is finite and non-zero, then S has Hausdorff dimension Q. Okay, and then it's denoted by dimension according to Hausdorff of S. So this was dimension of S. Okay, good. So let me present a theorem that tells you that in our case of subRiemannian manifolds will be easy for us to calculate the Hausdorff dimension because we have some stronger property, and this is the content of this theorem. So suppose we have a metric space, and suppose we have a Borel measure on M, and we assume that there exists Q, there exists C, and there exists R, such that for all points in the space and for all radii, we have, okay, radius, not all of them, but in the interval 0, R, so up to radius R, we have that the measure of the ball centered at P and radius R is bounded by R to the Q divided by, multiplied by C, is C R to the Q, and has a lower bound R to the Q divided by C. Okay, so assume that we have this property, then the Hausdorff Q measure of the ball radius R is finite and non-zero. Actually, we'll be more precise in the proof. So the dimension, and therefore the Hausdorff dimension of the ball is equal to Q. So if, for example, M is, then therefore, if M is countable union of ball of radius R, for example, if it is separable, then we can also conclude that the Hausdorff dimension of M is equal to Q. Okay. So we'll prove something stronger because we'll actually prove that this measure has the same bound like this. So we can put here. So in particular, it's finite and non-zero. Okay, let's prove this theorem. Proof. So let's fix a point P in M, and we call B the ball PPR, right? So we want to consider this ball. Right. So we have to prove two things. We have to prove that the Hausdorff measure is finite and non-zero. So let's prove that first, that the Hausdorff measure is finite. So first of all, let's fix some R in 0, capital R, and we let we consider delta is between 0 and R minus R. Okay. Now what we do, we take a maximum set, let's call it P1 Pn in the ball radius little r, maximal set, maximal collection of points, such that the distance between Pi and Pj is greater than delta for all I different than j. Okay, so we have the ball, and we take points. Okay, maybe we have this is the ball of radius r. This was inside the ball of radius capital R. So we've taken points. The distance of these points is at least delta. Okay, let's clarify the fact that okay, they exist by Zorn's lemma, but why they are only finitely many. So okay, let's clarify. Let's notice that such maximal set exist with finite n. And indeed, so what do we do? Okay, so for how we chose the delta, so this distance was this delta, and also we have this bound here, right? So if we take the ball of radius delta at the point, then the ball stays inside the big ball. So what we have, since we have that the ball, each ball pi delta is inside B, so we have this fact, and moreover, since they are delta separated, okay, if I take the balls of radius delta over 2, then they don't intersect. Delta over 2, intersection is empty for all I different than j. So up to taking even smaller balls, so the balls are all inside the ball of radius little r, in capital R, sorry, j. Okay, so these are this joint set. So then we have that there's this joint union of balls, and so they are all contained in P. Okay, so so what can you say? Okay, let's take the measure of this set, these two sets. So I take the measure. Okay, measure of the union pi delta over 2 is less than the measure of the R ball. So this was the R ball. So by the hypothesis assumption on the growth of balls, if this is less than CQR, in here, so these are this joint set. So I can just take the measure of each of the set, and each of the set we know that has up to a constant 1 over c. We have, so if you have n of them, and each of them has measure bounded by delta over 2 radius to the q, right? So now this tells us that n is finite for any delta. So this one is less than this, and this tells us that n is finite. Okay, let's continue. So next, since the collection of point pi is maximal, then we have the collection of balls pi radius delta. This is a cover of BPR because it was maximal. You cannot add any other point. Okay, then now we are going to use this sequence of sets to bound the Hausdorff content of the ball initially of this ball of this set. So what do we have? So the house. Okay, let's clarify what is the diameter of this set. So notice that the diameter. So if you take a ball of radius delta, every 2 points at the distance delta from pi, so that they are at most of distance to delta. Okay, and therefore now what we do, we consider the Hausdorff two-dimensional content with exponent 2 delta of this set. Now, so this is less than this possible cover. So for this cover, we have to sum the diameters of the pi delta q, q. Okay, by the so each of the diameter, right? It's so we have n of them, and each of the diameters bounded by 2 delta q. Now, okay, let me write this as up to a constant that you're very easy for you to calculate which one it is. I can write it this other way, so delta over 2 to the q, right? So I'm dividing by 2, I'm putting the constant c, which is the constant of the assumption here. Okay, I want to use it because now I want to use this bound here. So now if I write it like this, then I have that this is less or equal c prime, the sum of the measure of the balls center pi radius delta over 2. Okay, these balls, as we said, were disjoint. Was disjoint and inside the ball of radius capital R. Right? So this is less or equal in C prime mu of B. Okay. Now what we understand is that now this number here is finite and independent on delta. Okay. And therefore we have that the HQ of B, which I can write it as HQ of the union R less than R of B PR, this is less than C prime measure of B, which is finite. Okay, so up to this constant, we have this it's finite, and it's actually bounded by another this constant C prime times C times R to the Q. Okay, so this was for one bound. Now let's continue to prove that the Hausdorff Q measure of the ball is greater than 0, it's positive. So, okay, take delta epsilon and EI a cover, so such that the diameter, the EIs are all bounded by delta, and B is covered by this union of the EIs. Okay, and we moreover we take in such a way that it almost realizes the infimum that defines the delta content of B, right? So this fat plus epsilon, I can find something that is less than the sum of the diameter of EIs to the Q, right? Okay, so this is exactly coming from the definition of this delta content. Okay, now, first thing to notice is that for all I, there exists pi in EI, actually all, actually you can put any choice of PIs in such a way that EI is contained in the ball pi diameter of EI. This is true for actually every set. Now, so what we do, we do like this. Okay, B is covered by the union of the EIs. And now from this, we can say, okay, and it's also, this is covered by the union of BPI diameter of EIs. Okay. Now, Okay, let's take the measures of these sets. This is less or equal than the measure of the union, bi, pi, diameter of EIs. Now, by countable additivity, this is less than the sum of the measure of the balls. Very good. Okay. Now, let's use the assumption on the growth of balls. So this is less than sum, constant, radius to the q. And now, let's use here now, at this point, this inequality. So we have is correct, diameter is smaller, then have Hausdorff Q measure delta B plus epsilon is correct, exactly. On the other hand, this term we know that is also bounded by constant, no, 1 over the constant r to the q, which is positive, okay? So what we have, therefore, is that so this number is always greater than epsilon than this number. So now we have this is for arbitrary epsilon, we have the same bound, and therefore we also have it for the limit. Okay, so what we actually proved, we proved that so therefore we proved that the q-dimensional Hausdorff measure of the ball is also a non-zero, is non-zero, right? So actually what we proved, let me just wiggle it like this, it's up to a multiplicative constant, this is r to the q. So this is what, right? So, so in particular, so, and then we have the Hausdorff dimension, the Hausdorff dimension of h of b is equal exactly to q. Okay. So now this is what. So we finished the proof. Okay. Now let me say something about some terminology and rephrasing what we've proved for measures that satisfy this bound. Okay. So terminology. So a measure. Let's call it mu, with the property that there exists some q, there exists r, there exists c, such that, so I'm writing the same property that it was in the assumption of the theorem. So up to a multiplicative bound, upper bound and lower bound, we have the measure of balls behaves as r to the q. This is for all r in the interval 0, capital R. Then this measure is called Hausdorff Q regular. Okay, so we proved that if a metric space admits an Hausdorff Q regular measure exists on a metric space, then the Hausdorff dimension, the Hausdorff the Q measure. Oh, no, how did I call it? The Q-dimensional Hausdorff measure. The Q-dimensional Hausdorff measure on the set is alphas force Q regular. And in particular, the dimension is, the Hausdorff dimension is equal to Q. I will quickly show you a connection between the length and the Hausdorff one measure of the image of a curve. So here's the theorem. So suppose we have a metric space, and gamma curve and on an interval on M, so an injective rectifiable curve. So, and I stress the fact that we are assuming to be injective because we are talking about the image. Instead, like if you, for example, if you go around a circle twice, then the length will be twice the circle. Instead, the image will be just the circle. Okay. So under this assumption, then the length of the curve is equal to the Hausdorff one measure of the image of gamma. Okay, let's prove it. So proof. So first of all, okay, because we can reparameterize curves and the length and the image stays the same, we can assume that the we may reparameterize, and we can assume that the curve is parameterized by arc length. So if L is the length of gamma, then gamma is defined on the interval 0, L, value into M. Okay, so first let's prove this inequality, greater or equal. Okay, so for doing that, so we take delta, and then what we do, we divide the interval 0, L into enough parts, and disjoint intervals, so delta J, in such a way the diameter of each of the intervals is less than delta. Okay, of course you can do that explicitly. Okay, now since the curve is parameterized by arc length, then in particular we have that gamma is 1 Lipschitz, and therefore being 1 Lipschitz, we have the diameter of the image of these intervals is also less than delta. So in other words, this family of sets is a cover of the image of delta by sets of diameter less than delta. Right? So this gives us a bound on the Hausdorff one-dimensional delta content of the image of gamma. So this is less than sum of the diameters of gamma delta J, since we said this is since gamma was 1 Lipschitz, then this is less than the sum of the diameters of delta J, but this was just a covering of the interval 0L, so the total diameter is equal to L. Okay, so this gives the proof of the first inequality. Regarding the other inequality, so regarding this other inequality here, let me first give a lemma. And actually, as you see in the first part, we didn't really use that the curve was injective, so that's also true. And also, I'm going to make use of a disclaimer, a lemma that is actually true for all continuous curves. So the Hausdorff one measure of the image of an interval is always at least as the distance between the points. Okay, so indeed, so here's a small trick. So let's use this function phi of x, which is the distance function from x to gamma of a. Okay, so some things to notice is that first, this function phi is one Lipschitz. Like this is an exercise. And I will also make use of the fact that on the Euclidean line R, the Hausdorff one measure coincide with the Lebesgue measure. I leave also this as an exercise. Okay, now that we have this two property, let's calculate the Hausdorff one measure, the image interval. Now, since phi is Lipschitz, there is one here, and now this is equal of h1 of phi of gamma of a b, and now now consider that this object here, so this is the image by continuous map, so phi and gamma continuous. So this object here is a connected set. So this is an interval on R. And therefore, we can calculate the Hausdorff measure of this. And this is just the Lebesgue measure of this interval, which is at least as the diameter of this. Actually, it's equal. Actually, it's equal. The diameter of this set. And now the diameter is at least the distance of two of the points. So actually, you have for B you get for A you get 0, for B you get distance from gamma of B, gamma of A. So I proved this claim, and I'm going to use it for proving the other inequality in the theorem. So back to proving that the length of an injective curve, now is going to be important to this injective, is at least no more than the image, the Hausdorff one-dimensional measure of the image. So take a partition as in the definition of length, so T0, T1 up to Tn of the interval of definition. Then what we have is if we sum the consecutive distances, this is what one considers in the definition of length. Then by this claim to be just proved, this is at least, each of them is at least the Hausdorff one measure of gamma Ti minus 1, gamma Ti. Okay, now put things together and say that this is less than the Hausdorff measure of, sorry, this is, I have to put correctly, so this is of the image, so it's Ti minus 1, this is Ti. Okay. Okay, I claim that this is less or equal than the Hausdorff one measure of the image of gamma. Why? So here I'm using two things. I'm using that H1 is a measure, so it's additive. And gamma is injective. So these sets, when I varies, these are disjoint sets. Okay, so the measure of them, the sum of the measure is less than it is equal to the measure of the union. Okay, we can put equal. Okay, and this concludes the proof. If you liked the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel, clicking below.